played a tremendous role in organizing this whole workshop. So I'm personally and Abishai are very grateful to Colin, who's leaving Hebrew University and going to Cambridge, England.
Yes, so thank you for that introduction. Yes, I'm Colin DeGraff, and so I will be talking about looking at gas flows onto and out of galaxies within high-resolution simulations. Specifically looking at how gas penetrates into the galaxy and how the outflows from the galaxy actually escape out to the outer parts of the halo. So I'll give a little bit of motivation. Then I'll discuss how the flow is evolving with redshift and with distance from the galactic center. And then I'll talk about the direction that these outflows and inflows are going, particularly how they interact with each other. And then we'll get into gas recycling as well. Okay. So for the motivation, we have a pretty good sense of how mass flows onto halos. There are toy models that sort of show what you would expect for the dark matter mass accretion rate onto a halo, and then you can multiply that by the baryon fraction and get a pretty good sense of the baryon flow rate onto a halo. But then what happens when that gas is moving from the outer part of the halo down into the galaxy itself? So I'm going to be talking about using the VILA suite of simulations that were primarily run by Daniel Severino, who's here and will be talking later this week. So there's information on the simulations here. The main thing to know is these simulations are cosmological zoom-in runs, so we have very high resolution. It's about 35 to 70 parsec resolution, but it is in a cosmological volume, so we are able to model all of the inflows and outflows that are actually happening. So there are 34 galaxies. I'm mostly going to be looking at 8 of them, and we've got between 500 and 1,200 snapshots for each of those. So just to give you a sense, there's that toy model that I pointed out of the expected flow rate. Here I've plotted the flow rate from our simulations and overplotted in red the expected model, the toy model from Deckel et al. This is the evolution with redshift. If you divide out the dependency on the virial mass of the halo, so you can see the redshift evolution works out very well. And here's what happens if you divide out the redshift evolution and just look at how it evolves with the virial mass of the halo, and again, it matches very well. So this toy model does seem to agree quite well with what's happening, how things are flowing onto the virial radius. But then you want to look at what's happening inside that. So one of the main things that we find is we have inflows, which then trigger star formation. The star formation then triggers outflows, and we can see that happening here. So this is showing you inflow and outflow in red, and in green is the star formation just within the central 1 kpc. So the inflow and outflow here are looking at 10% of the virial radius. And in particular, if you just sort of look at this region, you can see there's a bit of a spike in inflow, spike in outflow, and a spike in star formation. And they seem to happen fairly simultaneously. If you then instead look at 0.2 RVIR instead of 0.1, then you can see the inflow actually does happen before the outflow, and the star formation happens in between. If you go out a bit further to 0.3 or to 0.4 times the virial radius, you can really see you have an inflow coming in, it makes it into the center of the galaxy, triggers star formation, the central kiloparsec, and then you have outflow that happens after that. If we then go all the way out to the virial radius, however, you see you no longer have this nice spike in the outflow. So what's happening is a lot of that outflowing gas isn't making it all the way out of the halo. It's only making it part way out, and then it comes back in again. So we're not getting complete escape information from these galaxies. So we can take a look at one snapshot, one example. In blue, you're looking at gas accretion. So if you just look at a solid line, you can see the inflow rate is relatively constant with radius. And so most of the gas that's coming in is making it all the way in. The outflow is mostly, once you get to about 0.2 RVIR, what happens after that is escaping all the way. And if you look at the dotted versus dashed lines, you can see most of the inflow is happening in the plane by a factor of a few, whereas most of the outflow is happening out of the plane, except in the very central regions, where you actually have a lot of outflow in the plane. And we'll get into that in more detail. in just a minute. So to really try and see this more statistically, we've now stacked all of the galaxies, all of these snapshots together. So when I do this stacking, I'm actually stacking the inflow rate scaled by the virial radius, the virial mass and the redshift according to that toy model that we already saw does a very good job. So we're not having any problems of stacking different redshifts together. That's all been taken care of here. So if you look in the outer region here, you can see inflow is higher than outflow, so these galaxies are still growing. And you can see the dotted line, which represents in-plane inflow, is much higher than the solid line, which is the out-of-plane inflow. So most of the inflowing material is coming in the plane, as you would expect. If you look in red at the outflow, it's the opposite. Most of the outflowing material is going out of the plane, which again, you would expect. But then you continue that all the way into the central part of the galaxy, and you can see as you get into the central region, the in-plane inflow and outflow both increase significantly. And so what's actually, and this is stacked across all the snapshots, so this isn't a short time scale event where just the outflow hasn't reached the outer regions yet. What's actually happening here is you have a lot of gas which is outflowing from the innermost part of the galaxy, or the edge of the disk of the galaxy, more specifically. But it's not fully escaping. It's only getting out to on the order of 20-30% of the virial radius. You only get out to about here. And that's why this is decreasing with time. With radius. As you're going out, a lot of this outflowing material actually gets turned around and comes back in. And what's particularly significant here is you see that signature of recycling, the outflows that aren't surviving all the way out, is primarily in the plane, not out of the plane. So in this plot, I've divided it up according to cosine theta of 0.5, which is admittedly a very generous definition of plane. But you can take a look at this at specific values of theta. So here you look at cosine theta of 0.9, so you're talking extremely out of the plane. It's fairly low. You see there's no signature of recycling at all. The inflows and outflows continue quite well. But when you then go in, you have cosine theta of 0.4. Now you start to see you are getting some recycling happening here. And then you go all the way into the plane where you're talking cosine theta of about 0.1, and now you're having dramatic amounts of recycling happen. So we're finding lots of recycling here on the order of the disk radius out to about 20-30% of the virial radius, and it's primarily happening in the plane of the disk, not out of the plane. So here's just an example, one of the snapshots. This is an edge-on picture of the galaxy. What's color-coded here is the inflow or outflow rate. So in yellow, you have outflowing material, and red is stronger outflowing material, and in blue is the inflowing material. So you can see the plane is here. So you have most of this inflow is coming in generally in plane. Most of the outflow is going out of plane. But you also have a lot of outflow that is still in this central part where the galaxy is, and it's in the plane of the galaxy. If you look at a face-on view, you can see that even more clearly. This is face-on, so everything you're looking at is in the plane of the galaxy. And you can see lots of outflow that is happening in the central region, but it's colliding with inflows, and so what ends up happening is that outflow ends up being brought back in again. So we could take a look at what happens with that stacking if you break it up into different evolutionary phases also. This is one of our galaxies, just as an example, looking at the mass in dark matter, stars, and gas in the central kiloparsec. And so you can see one of the features that we will often have, and others have done more work in this area, and I believe will be talked about tomorrow in the compaction and quenching day. But what happens is the central 1 kpc, you end up growing the amount of gas quite significantly, which is where you have sort of the onset of compaction here. And then quenching happens where you end up losing all of the gas in that central region. The star formation levels off. So if we sort of divide this up into 3 different phases, we say, originally we have a diffuse galaxy, then we have a compacting galaxy, then we have a quenching galaxy. We can stack all of the different runs from our suite of simulations together, and you see in the diffuse phase, you don't have any recycling happening. Doesn't matter if you look at in plane, out of plane, you just don't have any. Now part of this is biased because also the diffuse galaxies are small, they don't have a well-defined disk, but that's only going to affect what's in plane and out of plane. In terms of the total amount of recycling that happens, you don't have much. In compacting, you start to have significant recycling. It looks the same as what we saw before. And then in quenching, you have even more so. So we find that at late times, we are having a lot more of this recycling happen. Here, I'm looking at just the excess inflow and outflow, where I define the excess as the flow rate at a given radius minus the average flow rate between 0.5 and 1 RV. So this is really looking at what the excess on the small scales beyond what's coming in or going out at the large scales. And you can see the inflow and outflow pretty much agree with each other. So that's in keeping with the picture of this being recycling. Most of this outflow that doesn't make it out to the outer regions, there's an equal amount of excess inflow coming back in. So it's simply a question of this gas being ejected only out to 30-40% of the vela radius before it gets brought back in again. So one other way we can look at that is just look at the ratio of inflow at the vela radius to the inflow at an inner radius, which we'll define as a multiple of the disk radius, and escape being the opposite. So what is the outflow rate at the outer part of the virial region compared to the inner part. So if you look at this and you look at what's happening between 4 disk radii and the virial radius, you don't really have anything too significant. Most of what's happening at the inner regions, at 4 times the disk radius, still happening at the outer regions. So most of the outflowing gas escapes, most of the inflowing gas makes it in. But if you move into closer in, here's at 3 times the virial radius, 3 times the disk radius, and you can start to see that in the plane, at cosine theta close to 0, you actually have positive penetration. So there's actually more inflowing gas in the inner regions than at the outer regions, and it's the opposite out of the plane. And that's because of this significant amount of recycling that's happening in the plane of the galaxy. And as you go in closer and closer, you get that more and more extreme. So you have very high penetration in plane, very poor penetration out of plane, and the opposite for the escaping gas. Most of the gas escapes out of the plane. Here I'm just looking at, again, the penetration as a function, but now I'm looking at it as a function of the baryon fraction. So you can see what's happening outside half the virial radius is fairly, a lot of scatter, but it's simply there. But once you start moving in, and you're talking about going between 10% of the virial radius and the virial radius, then you see the more baryon dominated you are, the more recycling you tend to have. That's because your penetration is now greater than 1. The small scale inflow is greater than the large scale inflow. So here's a movie showing what's actually happening. So this is an edge-on view. So you're seeing most of the gas coming in, sort of generally in plane, most of the outflows being blown out of the plane. But you can also see even in the plane, you do have a fair amount of outflow that's coming out and hitting it. Again, the blue is inflow, red is outflow. So you can see you've got all this outflow that is coming out, colliding with the inflow, and eventually gets turned back around. That's happening in the plane. That's that recycling. Out of the plane, the gas just tends to make it all the way out. It doesn't have any strong inflows to collide with. So that's all we're seeing there. You can see the same thing. This is now a face-on view. So everything is in plane. And again, you see there's significant outflows being driven out that are then colliding with these strong inflows. There's a lot of interaction going on there, and that's what's causing all of this recycling. That's also why you don't have too much of this gas actually making it all the way out. A lot of it's just reaching these outer regions, these sort of 20-30% of the virial radius. And this happens consistently for all of these simulations that we've been running. So just to give you a couple little plots, just to give you a different way of seeing that, these are mall-wide projections. On the left are 2 different snapshots showing you inflow, where again you see it's mostly in the plane. It's concentrated in relatively small regions that are strong inflows. The outflow, however, you have it much more widely distributed, but you do have regions where you're in the plane and you have very strong outflow. So you have driven some of these in-plane outflows that collide with some of the inflows and come back in. There we go. So just to sort of summarize with a picture, one of the typical pictures for sort of the galactic fountain is where you have outflows going out of the plane, and then some of that outflowing gas turns around and ends up coming back in the plane. And so that's a sort of typical picture for this galactic fountain. What we're finding in our simulation is that's not the tendency to happen. Instead, most of what's flowing out in the polar direction just keeps on going. But if you look at a face-on view, you see in many cases you have these outflows colliding with inflows, just interacting with each other. And you also have cases where you have high angular momentum gas that's orbiting, that's driven out, but then because of interactions with the inflows, it ends up being brought back in again. And so this is a fairly different view of what's happening with the recycling than what you would typically find in these pictures. So I'm out of time, so I'll end here. Mainly I want to say we're finding significant amount of recycling, which is all happening at less than about 30% of the virial radius. But what's particularly significant that we're finding here that you don't find in a lot of cases is most of this recycling is contained within the plane. The more in plane you are, the more recycling you're finding. And the cause of that recycling is really the interaction between these outflows that are being driven out from the plane and colliding with the inflows on their way in. Thank you.
Okay, thanks. Could Dan Padnos set up? And meanwhile, we'll take some questions.
What's the mass of your galaxy and what's the box size?
Well, there are 34 of them, right? So typically we're talking about
the masses are at redshift 1 from
yes.
2 times 10 to the 11
up
to 2 times 10
12.
to the 12 solar
yes.
masses. And incidentally, the resolution is 2 times better than you said. So the worst resolution in that high resolution region is 35 parsecs. That's total mass.
Total.
Yeah. So do you see much mass dependence in your results? Like, is there any kind of structural differences for the lower mass ones compared to the higher mass ones, and any kind of redshift dependence?
Yes. So okay. Redshift dependence definitely. But like I showed, there was one where I stacked it based on sort of its evolutionary phase, and so you can in that case you saw. The diffuse, which is the high redshift, didn't have any of this recycling. Compact had some, and the quenched had the most. And that, if you stack it by redshift, you see the same sort of thing. Late redshift, you're seeing that. And if you stack by virial mass, you see the same thing. So all of these things are tied together, but yes, late redshift and high mass tends to have more of this recycling happening, the in-plane recycling.
It looks like Dan is having trouble setting up. Okay, good. Yeah. Okay, let's thank Colin again. Okay.
Flows from the galaxy actually escape out to the outer parts of the halo. So I'll give a little bit of motivation, then I'll discuss how the flow is evolving with redshift and with distance from the galactic center. And then I'll talk about the direction that these outflows and inflows are going, particularly how they interact with each other, and then we'll get into gas recycling as well. Okay. So for the motivation, we have a pretty good sense of how mass flows onto halos.
Played a tremendous role in organizing this whole workshop. So I'm personally and Avishai are very grateful to Colin, who's leaving Hebrew University and going to Cambridge, England.
Yes, so thank you for that introduction. Yes, I'm Colin DeGraff. And so I will be talking about looking at gas flows onto and out of galaxies within high-resolution simulations. Specifically looking at how gas penetrates into the galaxy and how the expected model, the toy model from Deckel et al. This is the evolution with redshift. If you divide out the dependency on the virial mass of the halo, so you can see the redshift evolution works out very well. And here's what happens if you divide out the redshift evolution and just look at how it evolves with the virial mass of the halo, and again, it matches very well. So this toy model does seem to agree quite well with what's happening, how things are flowing onto the virial radius. But then you want to look at what's happening inside that. So one of the main things that we find is we have inflows, which are toy models that sort of show what you would expect for the dark matter mass accretion rate onto a halo. And then you can multiply that by the baryon fraction and get a pretty good sense of the baryon flow rate onto a halo. But then what happens when that gas is moving from the outer part of the halo down into the galaxy itself. So I'm going to be talking about using the VLA suite of simulations that were primarily run by Daniel Severino, who's here and will be talking later this week. So there's information on the simulations here. The main thing to know is these simulations are cosmological zoom-in runs, so we have very high resolution. It's about 35 to 70 parsec resolution, but it is in a cosmological volume, so we're able to model all of the inflows and outflows that are actually happening. So there are 34 galaxies. I'm mostly going to be looking at 8 of them, and we've got between 500 and 1,200 snapshots for each of those. So just to give you a sense, there's that toy model that I pointed out of the expected flow rate. Here I've plotted the flow rate from our simulations and overplotted